The gradient theorem is an awful lot like the fundamental theorem of calculus. When we have some scalar function t, this is a scalar function, so this is going to depend on position, we'll say, so x, y, and z. The way to find the fastest rate of change for our scalar function t is to take the gradient of that scalar function. If we want to find out how much this function changes along a particular path, what we would do is we would take this and we would dot it with the direction, so a little tiny dl pointing in some direction that is arbitrarily part x, part y, and part z. If we want to find out the total change that we have as we go along, we would of course then have to integrate, and we would integrate, as we always do, from a up to b. What the fundamental theorem of gradients says is that when we add up all of these little tiny scalar bits, when all is said and done, this is going to wind up being equal to t evaluated at b. Note this is a scalar function evaluated at some vector position b, minus t of a, rather. Looks just like the fundamental theorem of calculus, and what this video is going to do is we are going to go through a particular calculation to show that this is true. We're going to take a particular scalar function, we're going to take the gradient of it, then we're going to integrate in order to show that this is true. The particular scalar function we're going to use is going to be in cylindrical coordinates, so we can take a line integral in cylindrical coordinates just to get some practice with that. So our function t of s, phi, and z is going to be what we're going to take the gradient of. And specifically, t is going to equal s, phi, z. This means that the gradient of t, which is going to be dt ds s hat, plus dt d phi hat, but because phi has units of radians and s has units of length, we have to pick up a 1 over s right here, plus dt dz z hat. For this particular function, we take the s derivative, s hat, 1 over s times the phi derivative plus 1 over the derivative with respect to z. So this gives us phi z s hat plus z phi hat plus s phi z hat. The particular path that we're going to wind up taking is a spiral, and this spiral is going to keep a constant s. So for all of it, s will equal 5. As we go up, s is going to stay 5. The path is going to stay 5 units away from the z-axis. Our phi is going to start at pi, and it's going to go back to negative pi. And our z is going to start at 0, and it's going to go up to 3. In general, our dl would have an s component, a phi component, and a z component. But in this particular case, because our s isn't changing, our dl is just going to wind up being the phi changing, so s d phi phi hat plus dz z hat. In order to do our line integral, though, we're going to want to come up with a relationship between phi and z. S is constant, so when z equals 0, phi has to equal pi, and when z equals 3, phi has to equal negative pi. So what we can say is that z is 3 divided by 2 pi times pi minus phi. Checking our answers real quick. Z equals 0 corresponds to this term being equal to 0. Z equaling 3 corresponds to pi minus negative pi is 2 pi divided by 2 pi times 3 is 3. But what we need at the moment is a relationship between dz and d phi, so we can say that dz is equal to minus 3 over 2 pi d phi. Now we're ready to combine our dl with our gradient of t into our equation in order to show that the fundamental theorem of gradients is true. We're integrating from 5 pi 0 to 5 negative pi 3. So we're integrating from 5 pi 0 to 5 negative pi 3. And we are integrating gradient of t dotted with dl. Well, our gradient of t is going to be this expression right here. Phi z s hat plus z phi hat plus s phi z hat. And this is going to be dotted with our dl. S d phi phi hat plus dz z hat. When we do this, because there's no s hat component, this will go away entirely. We can further say that because s is equal to 5, every place we see an s, we can put in a 5. And that will give us pi 0 to negative pi 3 of 5 from this s, z, d phi, plus 5 phi dz. Now it's going to prove useful to have this relationship between z and phi and dz and d phi. Because we've got a z equals stuff and a dz equals stuff, we're going to plug this into our z, and we're going to plug this into our dz. So we're now integrating from pi to negative pi, because that's what we're doing on our spiral. Oh, and we had a 5 in both terms, so we can go ahead and pull the 5 out. And we're left with z, which is 3 over 2 pi, pi minus phi, minus phi, times 3 over 2 pi. This minus sign is actually the same as that minus sign, and then this whole thing will wind up being d phi. We can pull our common factor of 3 over 2 pi out, giving us 15 over 2 pi integral of pi minus 2 phi d phi, of course. And we're integrating from pi to negative pi. This gives us 15 over 2 pi pi phi minus phi squared from pi to negative pi. So minus phi squared from pi to negative pi, that will just go to 0. Plugging in this, we wind up getting minus pi squared minus negative pi squared. So all told, this winds up being equal to negative 15 pi. That's this side. Now let's try this side. What we can do is we can just substitute in our beginning and ending points into this expression. So the question is, if we have TA, or TB, which will be 5 times, well, our final here is negative pi, and our final z will be 3 minus 5 times pi, and our initial z was 0, we are left with negative 15 pi. What this video showed is that if we have a scalar function, and if we evaluate the integral of the gradient of that scalar function, we can take that to be whatever it was at the final point, minus whatever that scalar function was at the initial point.